Hello all, welcome back. So we're going to continue our discussion on different theorems. So now we're going to discuss about Thevenin and Norton theorem and how to simulate them using PSPICE. So as we already know Thevenin and Norton theorem definitions, and we have already gone through the various numericals on Thevenin and Norton theorem. So if you want to go through the theory part, then you can access the videos, which is also the link is shared in the description, so you may go through those videos. So to start with Thevenin Norton theorem, first let us see what was Thevenin and Norton theorem. So in Thevenin Norton theorem, what we say is any circuit, any linear bilateral complex network can be converted into a simple network containing a series containing a voltage source and the series resistance. That is called as a Thevenin theorem. That means any circuit, suppose this is a circuit, and that circuit can be converted into a simple circuit, as we can see here, this circuit, which contains a voltage source and the series resistance. And if we are measuring the current across RL, so suppose if this is our RL, then whatever current that will appear here will be same as whatever current we will observe here. Now what are these voltage source and what is this resistance? The voltage source is the open circuit voltage source, which we can measure by removing the load and then determining the voltage, open loop voltage across this terminal. And the resistance is the equivalent resistance, which is calculated from the open circuit terminal, and while removing all the independent sources by their internal resistances, right? So that is called as R Thevenin, or equivalent resistance is called as R Thevenin, and the voltage source is known as V Thevenin. Now similarly, what is Norton theorem? In Norton theorem, same any linear bilateral complex network can be converted into a simple network now which contains a current source and the parallel resistance. Now the current source is obtained by determining the short circuit current across the load, and the resistance is similar as R Thevenin resistance, which is measured through the open circuit terminal, and then replacing the sources by their internal resistances. Okay. So now let's see how we can find out or how we can verify this theorem. So now as the circuit is ready, now if we run this and let's see what is the current across 20 ohm load is 2.554 ampere. Now let's verify the same using Thevenin theorem. So for determining Thevenin theorem, first what we have to do, determine the open circuit voltage. So let's put the circuit again here, and let us again put it here for the remaining terms. So now how to determine the V Thevenin? So normally what we do in theoretical calculation, we just remove this and determine the open circuit voltage, but the PSPICE software doesn't work like that. So instead of which, what we can do, we can increase this load to a very high extent, which will be similar to as open circuit, and then determine the voltage at the terminal. So let us consider this can be 200k, so which is a higher value, right? So now if we run the code, run the simulation and check the voltage, now this is our VTH, voltage across 200k is 63 volt, so this is our VTH. So now let us go to the Thevenin circuit and change the value to 63 volt, right? Now next, for ISC, that is your Norton resistance, now what we have to do, Norton current, so what we have to do, we have to put a short circuit here and then determine the current, right? But similarly in case of like in case of your VTH, we have increased the resistance. Now here also we have to do a similar kind of logic. That means we have to decrease this value to a higher extent, So suppose 0.001 ohm, which is a very small value, which is almost similar to short circuit. So now if we run the code and then check the current, and our current will be 13.5 ampere. So now let us make the source as 13.5 ampere. Okay, so now our Norton current is 13.5 ampere. Now when we already have VTH, when we already have ISC, now we can determine RTH or RN, because in case of like what we do in case of our theoretical calculation, we just open circuit the RL and then replace the sources by the Indian resistances. So in this case all will be short circuit and then calculate the value. But in case of PSPICE, we cannot determine the resistance value by any other option, because we have only voltage and current option for calculating. So now what we can do, we can determine RTH by VTH divided by ISC. That means the voltage across this terminal and the current across this terminal. If we divide them, V by I represents the resistance, resistance of that terminal. So that will be RTH or RN. So that means what we have is 63 volt divided by 13.5 ampere, which is 4.666. So what we can do, we can put this as 4.67 ohm. Similarly, this also as 4.67 ohm. Now both the Thevenin and Norton circuits are ready. Now what we can do, we can simply run the simulation and check what are the value, and just removing the headings. Now if you run this and check the current, then the current that we have obtained here is 2.554. Same current is obtained here, 2.554 in Thevenin circuit. Same current is obtained here, 2.556 in Norton circuit. So we have verified that the current that we obtain in any circuit can be determined by a equivalent circuit, which is a voltage source and a series resistance, or a current source and a parallel resistance, right? So the first one is called as Thevenin circuit, next one is called as the Norton circuit. So this is Norton and Thevenin theorem. Okay, I hope you have understood how to verify using PSPICE. So the logic is, whenever we have to determine VTH, we increase the resistance value to a higher extent instead of eliminating it, which is also similar to open circuit path. And for determining ISC, instead of putting a short circuit, what we do, we decrease the resistance to a very lower value, which can also be considered as a short circuit. So then we obtain the value of ISC, and the previous one we obtain the value of VTH, right? So now let's take an example on dependent source and see how it works. Okay, now let's check the dependent source numerical. So now we have, you can see, so this is a circuit where we have 2 volt, this is 2 ohm, then we have a 2 ampere current, this is 1 ohm resistor, then we have a voltage dependent voltage source, so that it is dependent on this voltage. So as you can see here also, we have made it connected to this terminal. That means we have, this is your dependency, and then the constant the amplification factor is 4, so the gain is considered as 4 here. Okay, and then we have 10 ohm, we have applied a 10 ohm of load. Now if we run the circuit and then check what is the current that is obtained here is 4.27 1.429. This is our current across the load. Now let's see about VTH and ISC. So now the same circuit has been considered here, and for determining VTH, the RL value is increased to a higher extent, and to determine ISC, that RLL value is decreased to a very much lower extent. Okay, now let's see what is VTH and ISC. So if we run this and find out the voltage, so the voltage across this load terminal is 30 volts, so that is why we have placed it as 30 volt in the Thevenin circuit. Now next, let us determine ISC. So for determining ISC, what we require is we have to calculate the current now. So if we run this, so the current is 2.727. so this is 2.727, which is given here. So now to determine the Thevenin or Norton resistance, it can be calculated like this. So we have 30 VTH divided by ISC is 2.727, so the value is 11. So that is why we are putting here the value as 11 here. Okay, so now if we run the simulation and check the current value, so the current that is coming across in the circuit of Thevenin, we are getting it as 1.429, which is same as the original circuit current. And similarly, in case of Norton theorem also, we are getting the same value of current, which is 1.428, slightly 0.001 lesser, so that we can consider as an error. So we are getting same amount of current by using Thevenin theorem and Norton theorem, and the original current that is obtained from the original circuit. Okay, so like this we can determine Thevenin and Norton theorem and verify any circuit which contains a dependent source. So I hope you have understood all the logics and how to determine or how to go for Thevenin and Norton theorem using PSPICE. So I hope that will be beneficial for you. So similarly, yes, one more point I would like to mention here is, so whenever we are having a Thevenin circuit, we can also go for the maximum power transfer theorem. So as per the maximum power transfer theorem, what it states, that maximum power will be transferred from the source to the load when load resistance is equals to source resistance. That means whatever value we are getting here for RTH, if we make the load similar, then the power obtained will be maximum. So the maximum power can be obtained by the formula VTH square divided by 4 RTH. So using that formula we can calculate the maximum power. Okay, so now if you want to go through the theory, I will also put the link for the theory class in the description, so you can also go through maximum power transfer theorem and the numericals that we have solved in our class. So thank you for patient hearing and reaching up to this far, and I hope this will be beneficial for you. So like this we will be explaining similar other examples in our future classes. So thank you for joining.